Okay, so here's a video about trees. So first I just thought I would draw a tree. Yeah, and actually maybe I even need to zoom out so you can see the whole thing. But this is a graph, as you can see, and it's a tree, and I haven't really told you what a tree is yet, but it's, well, it's a connected graph with no cycles. So I drew kind of a big one. And, I just figured that the picture might help us appreciate why such a thing is called a tree. Because, so a tree, I'm thinking of an actual tree, like the plant, right? If I were to represent such a thing as a graph, so to speak, it should be connected, like it's all in one piece. Otherwise, I would call it two trees, two separate plants. And trees tend to not have cycles in the sense that when a tree grows, it has like the main trunk, and then the branches go out, and sometimes the branches have other little branches sticking off of them. But the branches typically don't come back together, although, of course, there are some weird trees, like there's, that national park where there's a giant tree and the trunk has a hole in it that you can just drive your car through. But let's ignore trees like that. Most trees don't do that. Most trees don't sort of have a hole that you can go through. And if I were to represent such a thing, I would say it does not have a cycle. The tree that has a hole you can drive your car through, I would say it has a cycle, because there's the bottom, and then it splits into two pieces, and then it comes back together at the top of the hole. But anyway, we're not talking about that kind of tree. We're talking about this kind of tree. So that's, yeah, I mean, this is not real math talk that I'm putting in this introduction. I just want to help us appreciate why we would call such a thing a tree. Anyway, so for this lecture, I would say you should read the definition of cut vertex. Like, I'm not going to have you read all of section 3.1, but the definition of cut vertex and the definition of non-separable graph you should read. I'm not going to talk about those two things too much during this lecture, but I do also want you to read section 3.2. And in 3.2, they mention these things a couple of times, so you should at least know what they are before you read section 3.2. But it's not necessary to read all of section 3.1 before section 3.2. So that's the general area that I'm going to be talking about here. And so I basically already defined this, but if G is a connected acyclic graph, acyclic just means no cycles, then we say G is a tree. And right, so the first thing that I want to state and prove is Theorem 311, which is that G is a tree according to the above definition, if and only if we have the following. For all vertices U and V in the graph has a unique UV path. Unique meaning there's only one. So this is an if and only if statement. So when we prove it, let's prove both directions separately. So let's prove the forward direction. So I'm going to prove that if G is a tree, then this thing. So suppose G is a tree, and then what I'm going to do is I'm going to try to conclude that for all U and V, the graph has a unique UV path. So how would I prove that? First, I just stated my assumption that G is a tree, and then if I want to prove something for all vertices U and V, I should consider two vertices U and V and then show that no matter what U and V are, that G has a unique UV path. So that's what I'm doing. Let U and V be two vertices. um, then it's easy enough to see that G has a UV path because our assumption is that G is a tree, and part of the definition of a tree is that um, it's connected. So I'm assuming that G is a tree. That means, among other things, that means G is connected. And so for any two vertices, there's definitely a path from one to the other. So it's easy enough to see that G has a path from UV to the other, but or from U to V, I mean. What I really want is I want to conclude that G has a unique UV path, that there's only one. So it's good that I have one, but I'm not done yet. I have to show that there isn't more than one. So here I go. What I'm going to do to show that the UV path is unique is to suppose, for the sake of contradiction, and I'm not saying that I'm doing this for the sake of contradiction, but that's the way that the proof is going to go. I'm supposing the thing that I don't want to be true. I'm supposing that G has two separate UV paths. And what I'm going to claim is if G had two separate UV paths, then G would have a cycle. And yeah, I put this parentheses Y because there's something to think about there. Well, why is that true? I'm claiming that if a graph has two paths from one vertex to another vertex, then that graph must have a cycle. And I'm going to talk a little bit about why that is in just a second. But if you accept that it's true for the time being, that would be a contradiction. Like I said, this sentence here is like a little proof by contradiction. And the way this went is we assumed that if G had two UV paths, then G would have a cycle, and that's a contradiction because we're assuming that G is a tree and trees don't have cycles. So G can't have two UV paths, so G has just the one UV path, and so we're done with this part. We've concluded that G has a unique UV path. Now let's talk about this Y here. Once again, I'm just trying to explain the fact that if a graph has two paths from U to V, then that graph must have a cycle. Let me go momentarily to the next page here. So this is the fact that I'm trying to explain. If a graph has two UV paths, then the graph must have a cycle. And I've drawn a few pictures. Maybe if you're thinking about this in terms of pictures, then maybe this is the first type of picture that you think of. I see here's one path from U to V, and here's another path from U to V. And in this picture, it's really easy to see that there's a cycle. It's this cycle. The annoying part about this fact is that the two paths don't really have to look like this. Here I drew two paths that sort of don't really share any vertices except, of course, for U and V. But the paths might actually share a lot of vertices. For example, I could have one path looks like this, and then here I'll go in to draw the second path, and it's going to share all kinds of vertices. Like it can go here, and then maybe here, and then here, and then to V. And that's a really annoying picture to look at. Of course, I still see cycles. I still see, like here's a cycle of length 3. It's just these first 3 vertices. And I see more cycles. There's like the one that uses this edge and then goes back like this one. And then there's another cycle. There's this one. So what I'm saying is still true. It's just a more annoying picture to look at. And yeah, I made room for another picture here. So I could have my second path could sort of trace out part of the first path. Like my second path just follows along the first path, and it's not allowed to be the same all the way through because it has to be a genuinely different path, but part of it can be the same, and then maybe the second path goes somewhere else, and then, of course, it has to end at V because it's supposed to be a UV path. But I'm just pointing out the fact that these paths can they can sort of trace over each other along parts of the path. They can't be entirely the same, but they can sort of trace over each other for bits of it. And of course, the conclusion is still true. The conclusion is that this graph still has a cycle, and it does have a cycle. I see one here. Keep in mind that for a cycle, you're not allowed to repeat any vertices. Of course, a cycle is supposed to start and end at the same vertex, but other than that, you're not allowed to repeat any vertices. So we have to keep that in mind as we're looking for a cycle. But maybe a bit more formally, let me describe how to find a cycle. Look for the first vertex where the two paths differ, because like I said, the paths might be exactly the same up to a certain point, but like in this one. So I would say the first vertex where the two paths differ, what I mean is I'm tracing along the second path, and I'm looking for the first vertex that isn't on the first path. So in this picture, I would be talking about this vertex, because this is the first vertex where the second path has left. It has exited the first path. So I look at that, and then I know that the second path has to come back and touch the first path eventually because they both end at V. So even though the second path has gone somewhere else that's off of the first path, if I just keep following the second path, I know that it will end up back on the first path. And if I just look at say here, which is like right before the second path went off of the first path, I trace this until they meet again, then there's my cycle. And by the way, this plan works in all of the pictures. In the first picture, the second path immediately leaves the first path. Right? They're the same. The first vertex is U and U. The first vertex on the first path is U, and the first vertex on the second path is also U. But then the second vertex is completely different. The second vertex of the first path is here. The second vertex of the second path is here. And so from there, I just trace the second path until the next time it comes into contact with the first path, which is here. And there's my cycle. It also works in this picture. Once again, yeah, of course this is the most annoying picture, but say like say path P is this one on the bottom, and say P prime is this crazy one that goes like this, and then this, and then this, and then this. I would say that P prime does not trace along P like they do here. Like here, P and P prime, the two paths, like if P is this one along the bottom and P prime is the one that goes like this, that the first two edges of the paths are the same. They both use this edge, and then they both use this edge. In this picture, it's different. They don't use the same edge. So I would say that P prime has left path P already, and then you just look at the first time it touches P, which is right here, and then here's your cycle. So that's my explanation for why this part of the proof was true. If a graph has two UV paths, then the graph must have a cycle. And then, if you recall, that was our contradiction. Whoops. Okay. Now, before I forget, I haven't gone over this part of the proof. So just remember, what we're proving is that G is a tree if and only if it has this property. For any two vertices, there's a unique UV path. And I want to prove the backward direction, so I'm going to assume that between any two vertices U and V, there's a unique UV path. And then what I want to prove is that G must be a tree. So of course, to prove that it's a tree, I just have to show that it's connected and that it has no cycles. So here I go. State my assumption. So I'm going to suppose this, and then use that assumption to try to prove this. So here's stating my assumption. And then what I have to prove is that G is a tree, and that has two parts. First, let's talk about why G is connected, because that's one of the parts of being a tree. It's connected and acyclic. I just wrote that G is clearly connected, and I'll say out loud a bit more what the reasoning is. To be connected, I just need to know that between any two vertices, there is a UV path. Like for any two vertices, U and V, there's a UV path. And if I know that, then G is connected. But I do know that. In fact, I know more than that. I know that between any two vertices, U and V, there's a unique UV path. All I need to know right now is that there is one. I don't care about whether there's more than one or what. As long as there's at least one, then G is connected. So we're good to conclude that G is connected. What else do we need to know? Well, I'm trying to actually prove that G is a tree, so I'm happy that it's connected, but I also need to know that it's acyclic, that it has no cycles. And here I'm going to embark on another little part of the proof that is by contradiction. I want to conclude that G has no cycles, so what I'm going to do is I'm going to assume what I don't want to be true. I'm going to assume that G does have a cycle. So if G had a cycle, then I would get the following contradiction. If I look at two vertices on that cycle, and I'll draw a little picture here, and keep in mind that this picture is much, much simpler because we're saying it's a cycle, so all the vertices in the cycle are different. So the picture really does look like this. I don't have two things that are crazily zigzagging over each other or anything like that. I just have a nice clean cycle. All the vertices are distinct. It doesn't cross over itself or anything like that. So if G did have a cycle, then what I could do is I could let U and V be two vertices on that cycle, and in this picture it's very clear that there's two UV paths. There's one that goes around the cycle this way, and there's one that goes around that way. And that's what I said here. If G had a cycle, then for any two vertices U and V on that cycle, there would be more than one UV path. There might be even more than two, because there might be more to the graph than what I've drawn, but at the very least, there's these two paths, the one that goes around the cycle this way and the one that goes around the other way. And that would be a contradiction because we are assuming, once again, we're assuming that for all vertices u and v, G has a unique uv path. And so having more than one uv path would be a contradiction. So that's our proof that G can't have a cycle, because if it did have a cycle, then we would have vertices u and v with more than one uv path. So that can't happen, so G doesn't have a cycle, and so we've established the two conditions for G to be a tree. It has to be connected, and it has to have no cycles. Okay. So yeah. Sorry for this little definition in the corner, but I realized I didn't have it yet. A leaf of a tree is a vertex of degree 1, and that this is another, you know, a botanical term, right? In this picture that I drew, for example, this is a leaf, this is a leaf, this is a leaf. These are the vertices of degree 1. There we go. And they're also, you can think of them as the extreme ends of the tree. If you start at like the middle of the tree, and I'm being vague here, I'm not using like formal mathematical terminology, but you start at the middle of the tree, and then you follow one of the branches all the way until you have to stop. That's where the leaves are. And so this, I mean, again, it kind of makes sense to call these leaves because they're like the leaves of a tree. So that's what leaves are. And so here's a corollary, and I'm going to provide kind of a different proof for the proof of this corollary than the one that's in the book. So the corollary just says every non-trivial tree, non-trivial just means that it has more than one vertex. The trivial graph is the one that just has one vertex. And so what I'm saying is that every non-trivial tree has at least 2 leaves. And here's the proof. I'm going to consider a longest path in G. And I'm assuming that G is a non-trivial tree. And this is something that we've done before. We've considered a longest path in a graph. And I was careful to say a longest and not the longest, because there might be a tie for the longest path, and it doesn't really matter if there's a tie. I'll just pick one of them and call them P. The point is that there isn't any longer path than P. If there was an endpoint of P that had degree greater than or equal to 2, then we could find a longer path, right? Because here's a picture. When I draw a wavy line like this is like it's a path. There might be any number of vertices along the way. I'm not saying that there's an edge directly from here to here. Of course, there could be an edge directly from here to here, and then we would be just talking about a path of length 1. Or there could be any number of vertices along the way. When I'm drawing a path in a picture and I don't know how long the path is, I just draw a wavy line. But the point is, if I look at an endpoint, I can see that this has degree at least 1, because it has at least the edge from the path. If it had degree more than 1, then it would have to have a neighbor like this. Keep in mind, it can't have a neighbor, I'm going to draw a dotted line because this is not an edge. It can't have a neighbor going back on the path, because then we would have a cycle. So that can't happen. So if it has another neighbor, it must be something off of the path. It must be a brand new vertex. But then look, here's a longer path. I'm not supposed to be able to find a longer path than P. So that's what I said in this picture. If an endpoint of P had degree at least 2, then we can find a longer path. So in other words, this endpoint has degree only 1, and so that's a leaf. And also the same goes for this endpoint as well. If this one had another neighbor, then we could find a longer path. So this is also a leaf. So this end is a leaf, and this end is a leaf, and so we found 2 leaves. Okay. So let me get to the next theorem. Theorem 313, which is about the order and size of trees. If T is a tree of order n, so the number of vertices is n, and size m, so the number of edges is m, then m equals n minus 1. Okay, so we're ready to prove that. This is going to be a proof by induction on n. N is the order. The order is the number of vertices, and for this class, every graph has at least one vertex. So the smallest value of n that we're going to talk about is n equals 1. That's the smallest number of vertices any graph can have as far as we're concerned. So the base case is n equals 1. And there's really only one graph with one vertex. It has to look like this. It has the one vertex, and it can't even have any edges. In order to have an edge, you need at least 2 vertices to be the endpoints of the edge. So there's really nothing you can do. It just has to look like this. And so, well, it has 0 edges, because there's no room to draw any edges. And so m equals 0 and n equals 1, so m equals n minus 1, and so we're good. Okay, so that's the base case. Now let's do the induction step. So suppose n is at least 2. Then by the previous corollary, because remember the previous corollary is that every non-trivial tree has at least 2 leaves. And this isn't a trivial tree because n is at least 2. The base case was the trivial tree. For the induction step, we don't have a trivial tree. N is at least 2. So this is a non-trivial tree, so it has at least 2 leaves. And I don't really need 2 leaves, I just need 1 leaf. So let's just pick one of the leaves, it doesn't matter which one, and call it V. Then consider the graph T minus V. This is a vertex deletion. I'm deleting the vertex V from the graph T. And by the way, what does that even mean? I wrote that down here. If you have a vertex in a graph, say U is a vertex, G minus U is the graph with the following vertex set. First of all, the vertex set is just going to be the same vertex set as G, but without the vertex U, the one that you're deleting. The edge set is going to be all the edges of G except any edge that touches U, any edge that has U as an endpoint. That's what this says. For example, if G is this graph and U is this vertex, then G minus U, basically I cover this up with my finger, so there's no more U anymore. And also any edge that touches U is now gone. So the remaining graph just looks like this. So going back to what we were doing the induction step. We suppose that we have a non-trivial tree T, and it has a leaf V, and we're talking about T minus V. I drew a picture here. V is a leaf, so V has degree only 1. And so maybe we're sort of imagining in this bubble we have T minus V, and in the big square I've got T. So the only difference is that T has the vertex V, which is connected to one other vertex. And of course, when I consider the graph T minus V, there's no more V. So what I'm going to claim is that T minus V is a tree of order n minus 1. So let's talk about that for just a second. It's clear that T minus V has order n minus 1. We've removed exactly one vertex from a graph of order n, so we would get a graph of order n minus 1. What may not be so obvious is why this is a tree. So let's go over that. In order to convince you that T minus V is a tree, and keep in mind that T was a tree, but that doesn't, that doesn't necessarily make it obvious that T minus V is a tree. First of all, note that T minus V is acyclic because, well, I got T minus V, the way I got it is by starting with a tree, and trees are acyclic, and then I removed a vertex, and removing a vertex wouldn't suddenly make a cycle if there wasn't a cycle before. So the fact that T doesn't have any cycles definitely means that T minus V doesn't have any cycles. So that part is fine. We also need to check that T minus V is connected. That's the other requirement to see that it's a tree. To see that it's connected, and that's another reason why I drew this picture, take two vertices in T minus V. Say X and Y. And that's what I said here. Take two vertices, X and Y, in T minus V. And I'm going to claim that T minus V has an XY path. Why is that? Because in the original graph T, there was an XY path because T is a tree and T is connected. So T had an XY path, but then we might worry that when I remove the vertex V, that might mess with the XY path. But it doesn't, because the only danger is that this XY path could somehow go through V. If it went through V, then I would have a problem when I removed V. Then that path wouldn't be there anymore. But it can't go through V because V has degree only 1. If it was going to go through V, V would have at least two edges touching it, because in order to go through V, I have to go in and then I have to go out. So it's impossible that this XY path would go through V. And when I remove V, that doesn't mess with the XY path. So that's why T minus V is still connected. And that's why T minus V is a tree. Okay, so where are we? We've concluded that T minus V is a tree of order n minus 1. That means I can use the induction hypothesis because I know that this is a proof by induction, and so I'm assuming that any graph of order n minus 1 would have size whatever this is, where I replace n with n minus 1. In other words, the size of this graph is n minus 1 minus 1. So it's n minus 2. That's the number of edges in T minus V. And then the number of edges in T, because going back to this picture, if there's n minus 2 edges in this bubble, and there's just one more edge in T, then the number of edges in T would be this plus 1, so I get back to n minus 1. And so that there's n minus 1 edges in T, and that's what we meant to prove. Okay. Yeah, I'd better cut this off because I think I can't make videos much longer than this.